The sun has been obliterated from the sky, and an unlucky darkness invades the world. In the 20th book of Homer's Odyssey, a seer speaks those words during a feast. For centuries, classical writers like Plutarch and later modern astronomers argued this passage describes a specific physical event, a total solar eclipse. By the 1920s, astronomers calculated a date for it. They found that a total eclipse did occur over the Ionian Islands on exactly April 16, 1178 BCE. But historians have largely rejected this idea. The timeline requires precise astronomical data to have survived through pure oral tradition for 500 years before the epic was finally written down. The text itself is also ambiguous. The supposed eclipse happens while the characters are indoors, and the darkness is described more like a supernatural vision isolated to a single prophet. Trying to extract hard history from a single line of disputed poetry is a methodological dead end. To know if the eclipse is real, we need an entirely different set of evidence. We have to set that famous verse aside completely. The Odyssey contains several other passing references to the sky, specific notes about the moon, the planets, and the rising of certain constellations. Instead of treating these as literary scenery, we can test them as a rigid dataset of orbital mechanics. We can see if they mathematically align on a single day. To do this, we need a historical window. Classical estimates and archaeological dating of Troy give us a search range between 1250 and 1115 BCE. The epic repeatedly states that the climax of the story, Odysseus's return and the death of the suitors, happens precisely on a new moon. That gives us a concrete baseline. Inside our 135-year window, there are exactly 1,684 new moons. Let's call the day the suitors are killed day 0. Exactly 29 days earlier, according to the strict timeline of the epic, Odysseus set sail from the island of Ogygia on a makeshift raft. The poem tells us he navigates by watching the Pleiades and the late-setting constellation Baikouzis, while keeping the Great Bear, or Ursa Major, to his left. This star map shows us the problem with that instruction. The Pleiades and Baikouzis are located far apart on the celestial sphere. Because of the Earth's orbit, you can only see both of them simultaneously after twilight during a very narrow time of year. Specifically, Baikouzis sets late while the Pleiades are still visible only in late winter and early spring. Calculated for the 12th century BCE, that limits our navigational window strictly between February 17 and April 4. Our new moon on day 0 must fall inside this season. Applying this single constraint filters our baseline drastically. Any new moon outside that spring window is eliminated. Next, on day -5, Phaeacian sailors bring Odysseus to Ithaca, guided by the Star of Dawn. The morning star is the planet Venus. For this passage to be true, Venus must rise prominently in the sky before the sun. Astronomically, we can require Venus to rise at least 90 minutes ahead of the sun on this specific date in the sequence. When we apply this orbital constraint to our remaining dates, we eliminate roughly 2/3 of the surviving spring moons. The final test comes from day -34. The text describes the messenger god Hermes traveling to the far west, delivering a message, and immediately turning back. A well-known historical and allegorical theory equates Hermes with the planet Mercury. If we translate that myth into astrophysics, it describes asterigmos, the station where Mercury reaches its westernmost point in the sky relative to the sun before appearing to reverse direction. Our model requires Mercury to be positioned at this specific western turning point exactly 34 days before our target new moon. We are now mapping subjective mythology directly onto the rigid, predictable, and exact clockwork of the inner solar system. We have 4 independent variables: a spring new moon, a high morning Venus, a western turning point for Mercury, and a precise 34-day internal timeline tying them together. We can array the years from 1250 to 1115 BCE to see which dates satisfy all 4 conditions. Scanning down the timeline, year after year fails at least one of these planetary constraints. The orbital mechanics are unforgiving. Even years with alignments that fall just a few days outside our exact parameters are mathematically excluded. Out of 1,684 possible new moons, the filtering process leaves us with exactly one. Only a single date satisfies every celestial condition hidden in the text, April 16, 1178 BCE. That mathematical convergence brings us right back to the original mystery. April 16, 1178 BCE is the precise date of the total solar eclipse proposed by early 20th century astronomers. This star map details the sky over the Ionian Sea at 12:02 p.m. As the moon eclipsed the sun, the plunge into darkness revealed the sun's corona. Along the ecliptic, a 90-degree arc of planets, Venus, Jupiter, Mercury, Saturn, and Mars, suddenly popped into view. This rare visual reality matches the verse in Book 20, where the sun is obliterated and an unlucky darkness sweeps in. By testing only the secondary astronomical references, the data engineered its way back to the eclipse, completely independent of the disputed verse. The probability of fictional literary details accidentally aligning with the mechanics of the only visible total eclipse in over a century is exceptionally low. This math does not prove that a literal Odysseus existed, or that a room full of suitors was actually slaughtered on that afternoon, but it does imply something specific about the text itself. The epic's narrative timeline was structured deliberately around a verifiable astronomical framework. We still do not know how this advanced orbital data was preserved and transmitted across 5 centuries of oral tradition before the poet we call Homer finally set it down. Yet the advanced math is present in the verses. The Odyssey functions as a precisely calibrated narrative clock. With this astronomical timeline verified, the epic stands as a unique, surviving repository of historical data preserved from the 12th century BCE.